Today we are going to discuss the structure activity relationship of sympathomimetic amines. You already know what is sympathomimetic amines. Sympathomimetic amines are those endogenous compounds or drugs which produce activities in the body which mimic the stimulation of sympathetic nervous system. Again, what are sympathomimetic drugs? Sympathomimetic drugs are the group of drugs and the compounds, right, which produce such actions in the body which are normally produced by stimulation of sympathetic nervous system. So these compounds have their actions mimicking the actions of sympathetic stimulation. Now, usually you are not supposed to learn structure and function relationship between most of the drugs. But as far as sympathomimetic drugs are concerned, it's very important for you to understand the relationship between the structure and function of the drug. Because if you alter the structure of the drug, the function of the drug on the receptor is altered. Even duration of action of the drug is altered, right? Even the drug absorption and distribution in the body is altered. So let's concentrate on the structure of the drugs, sympathomimetic group, and their different altered compound. The primary structure is the parent compound is having a benzene ring or phenyl ring. This is a benzene ring. With this benzene ring, it is having ethyl chain. It is having ethyl chain, and with this ethyl chain, it is having amino end. So this structure is called, this is benzene ring, this is also called phenyl ring, right? And I must tell, this carbon is called alpha carbon and this carbon is called beta carbon. So this is the parent compound from which the sympathomimetic drugs are derived. This is the parent compound. Now, in this parent compound, we can see that to the beta carbon of ethyl chain, there is attachment of phenyl ring. This is phenyl ring as well as benzene ring. So this compound is called beta, because to the beta carbon, beta phenyl, phenyl is the ring, phenyl ethyl amine compound. So this compound or the parent compound is phenyl ethyl amine, right, compound, and this is its phenyl ring, this is its ethyl component of the chain, and here it is amino side chain, right? Now this is the primary structure of all sympathomimetic drugs. How this structure fit into adrenergic receptor to produce its action? Let me draw a cell on which there are many adrenergic receptors. Now, suppose this is a cell and here I put one adrenergic receptor . Now let's suppose this is the hypothetical structure of the adrenergic receptor, and of course all of you know adrenergic receptor is 7-pass receptor. So actually from here, now this is the point where the drug is binding, right? Now because drug is binding here, how this drug fits into this structure, right? Basically, this component of the drug, this benzene ring, that is fitting over here, benzene ring. And this component of the drug, which is ethyl group, that has to fit into this area. And in the end, you are having here, yes, amino end, which will fit here. Now listen carefully. This is how this drug is, primary compound is binding with the receptor. Is that right? Now listen, if this primary structure, the benzene ring, has some side components, then it will fit strongly into the receptor. Can it escape? No. But if, let's suppose, these two compounds are not added on the side of the benzene ring, then drug will bind and bounce back. So it will not bind here strongly. So for a strong binding of the drug on the receptor, we need that there should be some special groups on the sides of this benzene ring. Now what are these two special groups? Because if these two special groups are present on the side of the benzene ring, right, then this will bind here it will bind here strongly and for longer duration, and it will produce stronger stimulation to the receptor. Now let's see what are these two side special groups. As you know, this is our benzene ring or phenyl ring. Right here it has carbon number 1, carbon number 2, 3, 4, 5 and 6. Right? Now, actually, if we add here hydroxyl groups, right, then this compound is called, dihydroxy benzene ring. The other name for dihydroxy benzene ring, the other name for dihydroxy benzene ring is, yes, catechol ring. Catechol ring. So it means that if you take this primary compound and you add hydroxyl at carbon number 3 and carbon number 4 of the benzene ring, then you have converted benzene ring into catechol ring, and then this compound will be called catechol ethyl amine, or simply we call it catecholamines. So all those sympathomimetic drugs which are having hydroxylation and carbon number 3 and 4 on the benzene ring with ethyl group and amino end, those are called catecholamines. Now listen carefully. Look at the activity of these two hydroxyls. When these two hydroxyls are present, of course, the catecholamine drug will bind more strongly with the receptor. So action of the drug on the receptor will be increasing, and such sympathomimetic drugs which bind directly with the receptors, adrenergic receptors, and stimulate the adrenergic receptors, such sympathomimetic drugs are called direct acting sympathomimetic drugs. Those sympathomimetic drugs which directly stimulate the adrenergic receptors, they are called direct acting sympathomimetic drugs. Now you can understand, because all catecholamines are having these two hydroxyls, so all of them strongly bind with the adrenergic receptors, so all of them are directly acting sympathomimetic drugs. So these hydroxylation will determine that catecholamines are directly acting, yes, sympathomimetic drugs. Now let me tell you. For example, here is your heart. I don't want your heart to be black, but anyway it's there. There is your heart and this is sympathetic nerve ending. Right? You know that norepinephrine is stored in the vesicles, and from the vesicles, when sympathetic stimulation comes, norepinephrine is released, and then norepinephrine work on its receptor. Is that right? Now listen. Those drugs which directly stimulate the receptors, those drugs which strongly bind with the adrenergic receptors and directly stimulate the receptors, those drugs are called, yes, direct acting sympathomimetic agents or compounds or drugs. Opposite to that, there is another group of drugs which do not bind with the receptors properly, but these drugs are taken up by the sympathetic nerve endings. This is the second group of drugs which do not bind with the receptors well. They don't bind with the receptor well, but they enter into sympathetic nerve endings and go into neurotransmitter vesicles and increase the release of norepinephrine. Of course, such drugs, group number 2, which are going to sympathetic nerve endings and increasing the release of norepinephrine, of course, this increasingly releasing norepinephrine will also act on the receptor and produce sympathomimetic action. But such drugs are said to be indirectly acting sympathomimetic drugs. What are indirectly acting sympathomimetic drugs? Indirectly acting sympathomimetic drugs are those drugs, sympathomimetic drugs, which enter into sympathetic nerve endings and increase the release of endogenous catecholamines. Right? Now, and of course, there is another group, the group number 3, right? And this group number 3 has some activity to bind with the receptor, and they are also taken up into nerve ending. So the drugs which belong to the third group, they to some extent slightly they stimulate the adrenergic receptors directly. Secondly, some of this drug enters into nerve ending and increases the endogenous release of norepinephrine. So this drug is working directly acting as well as indirectly acting sympathomimetic drugs. This is also called mixed action sympathomimetic drugs. We'll go into detail later. So you understand, when I say to you there's a directly acting sympathomimetic drugs, it means this is a drug which will strongly bind with the adrenergic receptors and stimulate them. And when I say there's indirectly acting sympathomimetic drugs, I'm telling you that this drug is going to sympathetic nerve endings or into adrenal medulla and releasing the endogenous stores of norepinephrine and producing sympathomimetic activity indirectly. And there are some drugs which can bind to the receptors as well as they can be taken up by the nerve ending. So this produce direct sympathomimetic activity as well as by increasing the release of endogenous sympathomimetic drug, they produce endogenous release of catecholamine. They act as indirectly acting sympathomimetics as well. Such drugs are called mixed acting sympathomimetic drugs. So these are mixed acting sympathomimetic drugs. And here you have mainly working here and not working on the receptor. This is called, yes, indirect acting sympathomimetic drugs. Am I clear? Now come back to this structure. If these two hydroxyls are present, the compound will be catecholamine. Is that right? Any sympathomimetic drug which is having hydroxylation at 3 and 4 carbon of the third and fourth carbon of the benzene ring, such drugs as a group are called catecholamines. right? And of course, which are the members of catecholamines? Catecholamines have, yes, who will tell me the members of catecholamine? Norepinephrine, epinephrine, yes, epinephrine, yes, please, dopamine, and isoproterenol. Now look, these four are catecholamines. Three of them, norepinephrine, epinephrine, and dopamine, are endogenous catecholamine, right? They are produced within our body, and also they are available as drugs. And isoproterenol is a drug. It is not endogenously produced in our body. But these four compounds, norepinephrine, epinephrine, dopamine, isoproterenol, these are having catechol ring in their structure, so they are called catecholamines. And of course, now you know catecholamines are directly acting sympathomimetic drugs, because catecholamine have third and fourth hydroxylation on benzene ring, so they bind with the receptor strongly and they produce their action well. We also use another word when drugs strongly bind with the receptor and strongly stimulate the receptor. What is the word used there? We say drug has high potency. Look, when drug binds strongly with the receptor, we say there's strong affinity. But when drug binds the receptor as well as stimulates the receptor, we say drug is a strong agonist. It means if drug is strongly binding with the receptor, that even in low doses, it can produce high action. Even in low doses, it can produce high action, because even small amount will bind strongly. So we say drug has high potency. So what does it mean? All the catecholamines are highly potent drugs. Potent means as far as binding with the receptor, right? They have high potency. Now look, from all this discussion you can infer it. Look here, if we remove these hydroxylations, there is catechol, let us suppose from here we remove these hydroxylations. This hydroxylation is removed and this hydroxylation is removed. Do you think now this compound will bind strongly to the receptor or weakly? So when it will lose its direct, so what will happen? When it will bind with the receptor weakly, then it will become high potency drug or low potency drug? Right. Its affinity for the receptor will decrease, its activity on the receptor will decrease, and it will become low potency sympathomimetic drug. And it will be, as a direct acting sympathomimetic drug, it will fail. But there is something very good. When you knock off these two hydroxyls, drug become more lipid soluble. When you knock off these two hydroxyls, you remove them, drug become more lipid soluble. Am I right or wrong? Because hydroxyls are the negative charges, and by removing these hydroxyls, actually what you are doing? You are making the drug less polar and more lipid soluble. So such drug which is not having third and fourth hydroxylations, that can easily enter into nerve ending. Look here, you have to enter into nerve ending, it should be more lipid soluble. So such drugs which don't have third and fourth hydroxylation, they can enter into nerve ending and they can stimulate the release of norepinephrine from the nerve ending. They convert into indirectly acting sympathomimetic drugs. So again, compare this compound, this structure, right, and that structure. The primary difference is here third and fourth hydroxyls are present. In this structure, in this compound, third and fourth hydroxylations are absent. This structure is called, yes, catecholamine. And this structure is called, yes please, non-catecholamine. Non-catecholamine. Now, if someone asks you the difference in catecholamine and non-catecholamine, of course, first difference is the catecholamines are third, fourth dihydroxybenzene ring they are having. Non-catecholamine do not have catechol ring. They do not have third, fourth hydroxylation on benzene ring. So they are strongly binding with the receptors. So these are directly acting sympathomimetic drugs. So catecholamines are, yes please, you need to tell me, catecholamines are directly acting sympathomimetic drugs. I will write here, these are directly acting sympathomimetic drugs. And non-catecholamines are mainly, yes, they are indirectly acting, very good, indirectly acting sympathomimetic drugs. Is that right? No problem into this? Then another thing. You see, catecholamines have one more important thing. Because they are having hydroxyl group, catecholamines are highly polar compound. Catecholamines are highly polar compound. Now let's make a small, this is suppose your gastrointestinal system, right? Here is your liver, here is your general circulation, and here is your central nervous system. Let's talk some very fundamental things. Listen, if catecholamines are taken orally, actually catecholamines are never taken orally. Why? Let me tell you. When catecholamines are taken orally, come here, they are highly polar compound. Can they absorb well? No. And whatever little amount is absorbed, that will be destroyed by COMT and monoamine oxidase in the GIT mucosa, and also they will be destroyed by, yes, destructive enzymes in liver, monoamine oxidase, which is present in liver, and liver has some small amount of catechol O methyl transferase as well. Now listen, if you take catecholamines, right, if you take catecholamines orally, number one, they are highly polar compound, they will not be absorbed. Number two, whatever is absorbed will be destroyed by monoamine oxidases and catechol O methyl transferases. Especially catechol O methyl transferase enzyme. You know where it attacks? This enzyme, COMT enzyme, this enzyme will attack this hydroxyl. What is this? COMT, catechol O methyl transferase, will remove a hydroxyl and add their methyl group. So that is why this enzyme is called catechol O methyl transferase, an enzyme which attacks the catechol ring, remove the hydroxyl and add methyl group. Now, because this enzyme is abundantly present in our body, especially in GIT and liver, so what happens when catecholamines are taken orally? Number one, because they are highly polar, they are not absorbed well, and whatever is absorbed will be destroyed by these enzymes. So do you think significant amount of catecholamine will be reaching to the systemic circulation through oral route? No. So we say for catecholamine, oral bioavailability is very less. Oral, if you take the drug orally, catecholamines bioavailability is very less. That is why catecholamines are given parenterally. That is why that when you need to use catecholamines in a systemic fashion, you need to give a injection. Am I clear? Is that right? So catecholamines are given parenterally. Is that right? And they are not absorbed orally well, and their bioavailability is very less. Am I clear? Now imagine, compare it with non-catecholamine. Non-catecholamine, right, because they do not have these hydroxyls, so they are more polar or less polar? They are less charged or more charged? They are less charged. Because non-catecholamines, let me tell you examples of non-catecholamines. Examples of non-catecholamines are classically like ephedrine and amphetamines. There are others also, amphetamines. Now, ephedrine and amphetamines, they do not have 3,4 hydroxylations. It means they are more polar or less polar? They are less polar. So they are more lipid soluble. So they can be taken orally. This is first thing. So write it here. that these are given, catecholamines are given parenterally, and these are preferably given orally, because when non-catecholamines are taken orally, as they do not have these two hydroxyls, they will absorb better. And not only they will absorb better, there is one more thing. What is that? That, do you think this enzyme can attack non-catecholamines? No, because non-catecholamine do not have hydroxyl here. Non-catecholamine does not have catechol ring. And if non-catecholamine does not have catechol ring, how catechol O-methyl transferase can attack the non-catecholamines? So because non-catecholamines cannot be attacked by catechol O-methyl transferase, or non-catecholamines cannot be attacked by COMT, so duration of action of non-catecholamines will be prolonged. Duration of action of non-catecholamine is prolonged. So there is increased half-life, or there is increased duration of action by non-catecholamine. And of course, catecholamine has short duration of action, right? Catecholamines act in minutes. You know, catecholamine duration is counted in minutes, but non-catecholamine is acting over hours. Is that right? Now you understand. Three things we have learned. You remove these two hydroxyls. Number one, you convert the direct acting drug into indirect acting first. This is catecholamine. When you remove these two hydroxyls, you convert catecholamine into non-catecholamine. And of course, when catecholamine is converted into non-catecholamine, then non-catecholamine are less polar, right? They bind with the receptor less, but they are taken up more in nerve ending and help in release of endogenous norepinephrine. So non-catecholamines are indirectly acting sympathomimetic drugs. Number two, they are less polar, they are better absorbed from GIT. Secondly, because they don't have catechol ring, so they are not acted upon by COMT. So they have longer duration of action and better bioavailability. So they can be used orally. Is that right? Then another thing. You see, here is blood-brain barrier. There is blood-brain barrier. This is also a biological barrier made of lipids. Catecholamines are highly polar compound, right? Even though they are given parenterally, but can they go to central nervous system? No. When you give epinephrine or norepinephrine intravenously, they cannot cross the blood-brain barrier efficiently because catecholamines are highly polar compounds. Due to that reason, catecholamines, once they are administered parenterally, they do not have any direct action on sympathetic, they do not have any direct action in the central nervous system. But look at non-catecholamines. Non-catecholamines are not having hydroxyls. They are less polar. They can be absorbed from GIT. They can fool the COMT and go in high concentration there. But they have a problem. They cannot bind with the receptor strongly. But they can concentrate in nerve endings and release norepinephrine from there, indirectly acting. Plus, as non-catecholamines are more lipid soluble and less polar, they can cross blood-brain barrier. So they can go to central nervous system and they can produce, yes, effects and side effects in the central nervous system. That is why when we talk about amphetamines or ephedrines, which are non-catecholamines, they have very important actions and side effects in central nervous system. Is that clear? Let's have a break. So we were studying about structure and function relationship of the sympathomimetic drugs. And as we discussed that basic sympathomimetic parent compound is phenyl ring with ethyl and amine addition, right? So this is beta phenyl ethyl amine. And previously we have discussed that if there are two hydroxylations at third and fourth, it's catechol compound, catecholamine. If these are not there, then they are considered non-catecholamines. And when we were applying this structure to the receptor, then what we were talking about, that catecholamines, due to the presence of these hydroxyls, bind strongly to the receptors. But non-catecholamines, because they do not have hydroxylation and third and the fourth carbon of the benzene ring, so they do not bind strongly with the receptors. They have low affinity for the receptor and they bind and bounce back. Due to that reason, they are not direct acting sympathomimetic drugs. They are indirectly acting sympathomimetic drugs. Now we will come to another thing. Another characteristic of this molecule is that for a maximum direct sympathomimetic activity, the amino group and the benzene ring, amino group and the benzene ring, they should be separated by 2 carbons. Why? Because this area determines the primary binding of the drug, and this binding in this area determines the potency of the drug and affinity of binding, right? But this area, this part of the receptor, right, this determines intrinsic activity. This part determines intrinsic activity. To have a good intrinsic activity, it's very important that sympathomimetic drug should have its benzene ring and amino group separated by how many carbon atoms? 2 carbon atoms. So this is another important feature of structure and function relationship of sympathomimetic drugs. Now we come to very, very interesting phenomenon. What is that? You know, some of the sympathomimetic drugs bind with alpha-1 receptors, some of them bind more with beta-1, some of them bind with alpha-1, beta-1 and beta-2 receptors. How this happen? Why different sympathomimetic drugs stimulate different adrenergic receptor in a different fashion? Let's try to answer it. Let me draw different sympathomimetic receptor. Actually, this model receptor which I have made here, this is alpha-1 adrenergic receptor. What is this? Alpha-1 adrenergic receptor. Now I will draw the beta-1 adrenergic receptor and beta-2 adrenergic receptor, and you have to tell me where is the difference. You know, as kids find the difference in between the drawings. So I'm going to draw beta-1 receptor here and beta-2 receptor there, and you are going to tell me where is the difference. It is beta-1 receptor. This is beta-1 adrenergic receptor. And now I'm going to draw beta-2 adrenergic receptor. Yeah, this is beta-2 adrenergic receptor. Alpha-1 adrenergic receptor, beta-1 adrenergic receptors, beta-2 adrenergic receptor. Yes, where is the difference in them? The difference is in that points of the receptor where amino end binds. Alpha receptor has a small area where amino ends bind. Beta-1 receptor has larger area where, yes, amino end of the drug bind, and beta-2 receptor has very large area where what will bind? Amino end of the compound will bind. Now I will make, once you have appreciated this difference in the receptor structure, we will make a compound here. Look at this compound. Hydroxyl, so it is going to be catecholamine or non-catecholamine? It's going to be catecholamine. Okay, I will make it by, okay. What is this compound? Who will tell me the name of this compound? Yes. What is this compound? Okay. This is one compound. I will make another compound here. You compare the structure. Benzene ring, look, double hydroxylation, so it is also going to be catecholamine, CHOH, CH2, and only NH2. The difference in compound A, this is compound A and this is compound B. The difference in compound A and compound B is that it is having methylation on amino end, it does not have methylation, right? Okay, this compound is produced by converting this into catecholamine, hydroxylation here, and adding methyl group here. Is that right? Every one of you knows the name of this compound, and every one of you know the name of this compound. I'm not 99% sure, I'm 100% sure. Very good. The second one is, this B compound is epinephrine. Have you heard of it? And this is norepinephrine. The difference in epinephrine and norepinephrine is, epinephrine is methylated. You remember in previous lectures when we discussed that when norepinephrine is produced in the vesicle, the norepinephrine go to the cytoplasm. There is an enzyme called methyl transferase, which transfer a methyl group to norepinephrine amino end, and compound convert from norepinephrine to epinephrine. You know what is the easiest way to remember epinephrine? Epinephrine is methylated norepinephrine. Epinephrine is methylated norepinephrine. That's so simple. Is that right? Now listen carefully. This is our balanced compound, right? Epinephrine, look here. Attention please. This is its amino end. Epinephrine, look here, attention. This point, this end of the epinephrine can fit here. It can also fit here. It can also fit there. You are understanding? Because epinephrine amino end is methylated amino end, right? And it can fit into alpha 1 receptor. It can, yes, fit into alpha 1 adrenergic receptor, and this amino end can fit into, yes, beta 1 adrenergic receptor, as well as this end can fit into, yes, beta 2 adrenergic receptor, even though it fit into this part and remaining is empty. But epinephrine can bind with alpha 1 adrenergic receptor, as well as it can bind with beta 1 adrenergic receptor, as well as epinephrine can bind with the beta 2 adrenergic receptor. Is that right? Due to this reason, epinephrine has which actions? Epinephrine has alpha 1 actions and also beta 1 action and also beta 2 action. We can say epinephrine is a balanced sympathomimetic drug. This term I'm telling you, made myself. That's a balanced drug. Balanced in a way, it works on all adrenergic receptor with the almost same affinity. Am I clear? There's no problem, right? Now you imagine, look, attention please. From this epinephrine, you remove methyl group. You remove methyl group, what is the result? Norepinephrine. Now norepinephrine can fit with alpha 1 receptor. You know, this point can fit into alpha 1 receptor, can also fit and stimulate beta 1 receptor, but to have stimulation on the beta 2 receptor, you need relatively heavy. So you have knocked out this. When you remove this methyl, right, actually this drug loses its action on the beta 2 receptor. Listen, the principle is this. Attention please. Look at these points. amino end, more heavy, amino end, more it become heavier, beta 1 and beta 2 action become increased. And amino end, you make it lighter, it will have more alpha 1 action. We can make it like this. This is the balanced epinephrine, is that right? If you are making amino end of the drug lighter, action will move to this side. And if you are making amino end heavier, actions will move in that direction. It's so simple. So, norepinephrine has ability to stimulate alpha 1 adrenergic receptor, has ability to stimulate beta 1 adrenergic receptor, but does not significantly stimulate beta 2 receptors. So what are the actions of norepinephrine? Alpha 1 actions, beta 1 actions, and very little beta 2. It's so simple. If next time someone asks, tell the physiological and pharmacological actions and the difference of these actions between epinephrine and norepinephrine, it's so simple. When you tell about the pharmacological actions of epinephrine, tell all the alpha 1 adrenergic actions in the body, all the beta 1 adrenergic action in the body. For example, alpha 1 action like vasoconstriction, all beta 1 action. For example, one of them is cardiostimulation, beta 2 action like bronchodilation. But when you go to norepinephrine, it has alpha 1 action like most of the vasoconstriction. It has beta 1 action, it is cardiostimulation, but it is not bronchodilator. Is that right? It is not relaxing the uterus, which is beta 2 action. It is not releasing glucose from the liver, glycogenolysis, which is beta 2 action. Am I clear? Now it's so simple. Now let's produce another compound in which we make amino end heavier. Right? Hydroxyl, and CHOH, CH, and here I put now NH, CH2, NH, CH, okay, CH3 and CH3. Now what we have done, here now we have changed the amino end. Amino end has, what are these? Has become heavier. Because it has become heavier, it is so heavy it cannot fit into alpha 1 well, but it will fit very well into beta 1 and beta 2 receptors. So naturally, intuitively, you can tell me that this drug will have very little alpha 1 action but heavy beta 1 action and heavy beta 2 action. Is that right? And can you tell me the name of this drug? Isoproterenol. What is the name of this drug? Isoproterenol. Am I clear? No problem? So what happens in isoproterenol? That at the amino end there is substitution with a heavy alkyl group, and due to this reason, because amino end is very heavy, so it loses alpha 1 action but it keeps the beta 1 and beta 2 action. Am I clear? No problem. Now I will make one more. Right. This is of course catecholamine, CHOH, CH2, and now we'll put amino group here, NHC, CH3, CH3, CH3. So it becomes even more heavier. Amino end has become really very heavy. It is so heavy that it will bind with beta 1 weakly, because beta 1 cannot accommodate, alpha 1 cannot accommodate such a heavy amino substitution at all. Beta 1 bind it very little and beta 2 action remain very strong. So now this drug with very heavy amino substitution, it has very little beta 1 action, but real action is beta 2. Is that right? What is the name of the drug? You know it. Terbutaline. Very good. Salbutamol. All these terbutaline, salbutamol, albuterol, all those drugs which are strong beta 2 stimulant have very heavy amino groups. Is that right? So I should write the drug name here. Terbutaline. You know, it is having a strong beta 2 actions, and because it has strong beta 2 stimulatory action, of course it is very commonly used as bronchodilator in patients with asthma. What is the advantage? You play with the molecules and you get advantages or disadvantages. What we have played, look here, this primary structure was come here. You have norepinephrine, is that right? Or you have epinephrine. What did you do there? You made this end very, very heavy, so it lost alpha 1 action. When you want a patient, you have a patient with bronchospasticity or patient with asthma, you want to do bronchodilation, but you don't want alpha 1 action. You don't want beta 1 action. So to remove the alpha 1 action and beta 1 action, you simply make this end very, very heavy. So alpha 1 side effects are lost. Even beta 1 unwanted actions are less. But when you give this drug in very high concentration, then it's also start binding significantly to beta 1, and beta 1 side effects will start appearing. That is why these salbutamol or terbutaline, albuterol, these drugs in higher concentration start cardiostimulation. Otherwise, in low concentration, they are good bronchodilator with some other beta 2 action like tremors or beta 2 action on the liver and producing high glucose release from the liver by glycogenolysis. Is that right? No problem into this? So this is how you understand now that differences between norepinephrine, epinephrine, isoproterenol and terbutaline. What we have learned up to now is that as you are making amino acid end heavier, you are losing the alpha 1 action and getting more beta actions. And if you make it very heavy, even beta 1 action is lost and strong action is on beta 2. But as you keep on making amino end lighter, beta actions are reducing and alpha 1 actions are more. Right? Let's have a break. Now let's play some tricks. And you know, these are norepinephrine, epinephrine, isoproterenol and terbutaline, all of them are catecholamine. Let's alter their structure and get some non-catecholamines. For example, first we alter the structure of epinephrine, right? And how we alter the structure of epinephrine? First I draw the epinephrine and then we produce some alteration in epinephrine structure to get some non-catecholamine. Now this is, of course, your, what is this? What is this compound? This is epinephrine. And now what we do with epinephrine, that just knock off these two hydroxyls. Remove these two hydroxyls. Is that right? From norepinephrine, you remove these two hydroxyls and plus you add a methyl group here. Remove these two hydroxyls and add a methyl group here. Now we see this is a different compound and it will have different pharmacodynamics and different pharmacokinetic property, right? Number one, step by step we'll move. When we remove these two hydroxyls, the drug becomes less polar and more lipid soluble. So it means this drug can cross GIT barrier, it can be absorbed from the GIT, it can also cross blood-brain barrier, right? This is one thing. Secondly, first of all, what is the name of this compound? This compound is ephedrine. This compound is ephedrine, right? Now, when you remove these two hydroxyl, it becomes more lipid soluble, it can absorb from GIT, it can cross blood-brain barrier, it can act in central nervous system. Secondly, when you are removing these hydroxyls, it is no more catechol ring. because it is no more catechol ring, then this enzyme, you know what is this enzyme? Catechol-O-methyl transferase. This attacks this component of the catechol ring. But because we have removed the hydroxyl and it is not catecholamine, it does not have catechol ring, so catechol-O-methyl transferase cannot attack this compound. So this compound will not be destroyed in GIT or in the liver. So duration of action of the drug will become more, and oral bioavailability of the drug will also become more. So it can be better absorbed orally, because it is not destroyed by COMT in the GIT or liver. So oral bioavailability is more. Secondly, because these two hydroxyls are not there, so drug does not bind properly with adrenergic receptors. So it does not have direct sympathomimetic action. It has very little direct sympathomimetic action, but it has, because it is non-catecholamine, it can have more indirect sympathomimetic action. So we can say ephedrine is non-catecholamine, which can absorb well orally, right? Which can cross the blood-brain barrier and act in central nervous system, right? And it is indirectly acting sympathomimetic drug. Another thing, because we added a methyl group here, by addition of methyl group, we make this compound more lipid soluble. And when we make this compound more lipid soluble, again that helps in absorption from GIT and help in crossing the blood-brain barrier and having more action in the central nervous system. Is that right? Another thing, as you know, this is the enzyme monoamine oxidase. Monoamine oxidase enzyme is sitting on the alpha carbon, and then what it is doing? It is oxidizing the beta carbon hydroxyl. Now what we do when we put methylation here, this enzyme cannot bind with the compound, because this enzyme monoamine oxidase binds here. Because monoamine oxidase cannot bind there, you know, its mouth is closed. This is monoamine oxidase weeping. Why? Because it cannot bind here well and cannot attack here. So monoamine oxidase failed to destroy ephedrine. So it means that when ephedrine is taken up into adrenergic nerve endings, then within the adrenergic nerve endings, monoamine oxidase cannot destroy this drug efficiently, so it will stay in the nerve ending for longer duration and it will produce indirect sympathomimetic action for longer duration. Is that right? Any question up to this? There's no question. Now we play another trick. Let's modify norepinephrine and convert into another non-catecholamine. Now this was your amphetamine. Now we are going to make another compound. This is also non-catecholamine. This compound is also non-catecholamine. What we do, this is its benzene ring. We have removed these two hydroxyls. These two hydroxyls here we have removed. So it means we convert the catechol compound into non-catechol compound. Please correct, in ephedrine we have removed this hydroxyl. In ephedrine, no, it is there. It is okay. Now we have to come to the new compound. What we have done, that we have taken the norepinephrine, removed third and fourth hydroxylation, plus we have also removed, yes, another hydroxylation from this point. So there are 3 hydroxyls have been removed. Again, you took the norepinephrine, removed the third and fourth hydroxyls, and also removed the hydroxyl from beta carbon. Is that right? When so many hydroxyls are removed, it becomes highly lipid soluble. Is that right? Very good oral absorption and very good crossing from blood-brain barrier. Is that right? And of course, it is not directly acting sympathomimetic drug. It is indirectly acting sympathomimetic drug. And because this hydroxyl is not there, can monoamine oxidase attack here? It is just like this. Someone does not have ear. Can you remove his ear? No. So monoamine oxidase cannot attack here. COMT cannot attack here. So drug absorption from GIT and bioavailability from GIT become very good, and destruction of the drug but COMT and monoamine oxidase is far less. Due to that reason, this drug has a long duration of action. And remaining thing is the same, that CH, as we added methyl here, we will also add methyl there. Is that right? We have also added the methyl there. And what is the last thing there? Yes? NH2. And what is the name of this drug now? Yes, who will tell me the name of this drug? This is non-catecholamine. This is amphetamine. So this was two examples in which I have shown you the structural and functional difference between catecholamines and non-catecholamine. Now, do you have any question? Do you have any question? No questions. Now I will rapidly review something, right? You will tell me. If these two hydroxyls are present in the structure with the benzene ring, it is catecholamine or non-catecholamine? It is catecholamine. Catecholamine have strong direct acting action or non-catecholamine have strong direct acting action? Catecholamine. Okay. In non-catecholamines, because these hydroxyls are not there, they will be more lipid soluble or less lipid soluble? Okay. Now I will ask in another way. Right? You have to tell me drug is catecholamine or non-catecholamine. There is sympathomimetic drug which is well absorbed from the GIT and going to central nervous system. It is catecholamine, non-catecholamine? Non-catecholamine. There is sympathomimetic drug. It has to be given parenterally and short duration of action. Catecholamine. There is sympathomimetic drug which can absorb orally, have long duration of action and go to the central nervous system. Yes, non-catecholamine. Okay. There is a drug which is catecholamine, I'm telling you, which is catecholamine. It has very, very heavy amino substitution. It is strongly alpha 1 action or strong beta 2 action. Beta 2 action. There is another drug, an amino end is very light. It has strong alpha 1 stimulation or it is strong beta 2 stimulation. Strong alpha 1 stimulation. Now I will tell the drug and you will tell me the name. Okay, I will tell the action and you will tell me the name of the drug. The profile of the drug is, there is a sympathomimetic catecholamine which has equal alpha 1 action, beta 1 action and beta 2 action. What is the drug? Epinephrine. Very good. It is epinephrine. There is another drug. It has a strong alpha 1 and beta 1 action, but beta 2 is very less. This is norepinephrine. Very good. There is another drug in which beta 1 and beta 2 actions are very well, but there is very little alpha 1 action. Isoproterenol. Very good. And if I say there is a drug which has very little beta 1 action, but strong beta 2 action. What is that? Terbutaline. That's great. Class dismiss. Thank you.